Welcome to 17.3. 17.3 is the last section that we're going to cover in this course, and it's the final of the three big theorems that have to do with vector calculus. The first theorem that we saw was Green's theorem. Green's theorem looked at the relationship between the vector line integral around a two-dimensional boundary and related that to the scalar curl of the double integral over that region, all in two dimensions. Then last section, in 17.2, we saw Stokes' theorem. Stokes' theorem is exactly like Green's theorem, only it's been lifted up into three dimensions, so that you're talking about relating the boundary, the line integral over the boundary of a surface with the double integral of the curl of a vector field over that surface. Finally, divergence theorem is going to bump it up one more dimension, essentially. And in the divergence theorem, our regions, instead of being surfaces in R3, they're going to be whole volumes in R3. And we'll see that when we state the divergence theorem. So our goals: first we have to define what divergence is. We're talking about divergence theorem. We're going to talk about a geometric interpretation of divergence. And then I'm going to state and apply the divergence theorem, meaning that I'll give you the definition, and then we're going to look at an example. So let's say that we have a function f of x, y, z. In this case, it's a three-component vector function, but it need not be in R3. It could be in R2 as well. We define it as the first component function, the second component function, and the third component function. This is just to emphasize the fact that the outputs are in R3. Oh, maybe you don't know that notation. Anyway, doesn't really matter. In R3. The divergence of f, usually we abbreviate it as the div of f, is equal to, there are two ways of thinking about it. One way to think about it is that it's the dot product of the gradient operator with f. That's sort of a funny way to think about it. What is this notation telling us? So recall from last time that we can think of this gradient as an operator given by the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So if I think of this as a vector operating on my function f1, f2, f3, what does this dot product give me? It's the product of the first terms, and in this case, that product is going to be the operation of the partial derivative with respect to x on the first component function, plus the partial derivative of f2 with respect to y, plus the partial derivative of f3 with respect to z. Recall, because this is a dot product, this is a sum. So it's a scalar. Well, maybe I shouldn't call it a scalar, but it's not a vector. It is a scalar, not a vector. That it's really tempting to write this as this, right? As a vector. I will do it incorrectly 2 times in my life. No, not in my life, maybe 2 times today. And now that I pointed out that that's what you want to do, you will never do it, right? That you need to know that this is always, the divergence is always going to be a scalar, and it's not going to be a vector. So this is our formula. This is our formula. So the divergence of f is given by exactly what I wrote down here. Oops, look, I almost wrote it as a vector. You aren't even here to correct me. The partial of f1 with respect to x plus the partial of f2 with respect to y plus the partial of f3 with respect to z. Just as a side note, let's say that our function only had 2 components. Let's say it was in R2, our vector field. Divergence also applies. So unlike curl and scalar curl, where we had 2 different definitions depending upon whether our vector field was in R2 or R3, for divergence, it's the same thing. We would just get rid of this third component. Yeah, you want to see an example? Let's do a quick example. I don't think that this concept is that hard. but it's good to compute things. So let's say we have a vector field in R3 given by xy squared, comma, z cubed, xy, comma, y to the fourth. Then if I want to know what is the divergence of f in this case, I'm going to take the partial derivative of this first component with respect to x, and that gives me a y squared. And then I'm going to add the partial derivative of the second component with respect to y. And so treating z and x as constants, that's going to give me z cubed x plus partial derivative of the third component with respect to z. There are no z's here, so I treat the y to the fourth as a constant, which just gives me 0. So I might not include that when I write out my divergence. I think it's a relatively straightforward computation now that we're masters of partial derivatives. What is cool about divergence is the geometric interpretation. So let's say that we have, I'm going to illustrate it as a two-dimensional vector field, but the same thing is true for a three-dimensional vector field. It's just really hard to draw. I don't like drawing three-dimensional vector fields, so I'm not going to draw a three-dimensional vector field. Let's say that our vector field is something like xy. All this outward pointing vectors. So when you, colloquially, what does it mean to diverge? It means to go apart. And what divergence measures is the net flow through a particular region. So let's say that this is my region R. And I want to know what is the divergence of F over R. It's given by the net flow through R. R is for rectangle, maybe it's for region. What do I mean by net flow? So I'm thinking of F as a vector field that represents flow. So I could think of this as like a pond or it could be a magnetic force field. It could be, for me, I like to think of terms of water. Water is something I'm used to dealing with. And really what I'm asking is more water flowing into this region or is more water flowing out? And so it's going to be, my net flow is going to be given by my outflow minus my inflow. That's a weird way to think about it. But this is something that does have positive divergence because my outflow is greater than my inflow. Why do I think that my outflow is greater than my inflow? Well, in this case, I see that the vectors going in on this side are going to be little bitty vectors, right? And the vectors that are going out are going to have greater magnitude. So that's telling me that my inflow is less than my outflow. And so that means that I have positive divergence. So this is an example where R has positive divergence. Another way to think about it, and this is actually the visual that I prefer, and you can decide which visual you like the best. I actually like to think of what is the motion of my R under this flow. So let's say this is my original region R. If I were to place this, like if this were colored water, if my colored water took up this rectangle, and I looked at what happened over time, what would happen to this region, we would see that if I sort of followed the paths of these vectors, that my region R would expand, right? Following this vector field, these vectors are going outwards. And so this would be like R at time 2, if this is R at time 1. And this expansion exactly correlates with positive divergence. So this is the graphical interpretation of divergence. Obviously, I want you to be able to compute it algebraically, but it's nice to be able to look at a vector field and say that, at different places in the vector field, you might have positive divergence and you might have negative divergence. This one's uniform, that it's always going out, but you could have some places contracting and some places expanding. So the places where it's expanding, those are places of positive divergence. And the places that are contracting, those are of negative divergence. And this is also true for three-dimensional vector fields. So you can imagine in 3 dimensions if I have some box instead of a flat region, and if all of these vectors were pointing out in every direction, you could say, what happens to this box under the vector field? Does the box get bigger or does the box shrink in?